What happens when our most advanced space monitoring technology captures an image that, just totally defies explanation, only for the data feed to be severed at that precise moment? On June 18th, NASA's live stream tracking 3I Atlas, our solar system's third interstellar guest, transmitted a single, baffling frame. It showed an object with characteristics that appeared, honestly, unnervingly artificial, then nothing but static. The official report cited network failure, but cryptographically verified data from independent archivists confirms the image is real. So what was that razor-sharp glint in the void? Let's analyze the data together. The initial discovery. The story begins with a technological marvel of planetary defense. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes better known as ATLAS, triggered an alert. This NASA-funded system, with University of Hawaii's Larry Deno as its principal investigator, scans the entire night sky every 24 hours. Its primary mission is to find near-Earth objects, but on this day, its algorithms flagged something extraordinary. The object's trajectory was hyperbolic, a clear mathematical signature indicating its velocity was far too great for it to be a member of our solar system. It was on a one-way ticket just passing through. The global astronomical community immediately mobilized, and within a day, the Minor Planet Center officially designated it 3Y Atlas, confirming it as just the third interstellar object ever detected. While early images showed the familiar coma and tail of a comet, its origin story was anything but familiar. This was an artifact from another star system, a rare opportunity that our technology, far more advanced than during the 2017 flyby of Oumuamua, was finally ready to seize. The anomalous frame. This is the moment a routine observation devolved into a profound enigma. The final frame broadcast from NASA's feed, captured at precisely 03:1712 UTC, initially seems unremarkable. The faint glow of the comet's nucleus, enveloped by its gaseous coma, is set against the cold vacuum of space. But in the lower left quadrant, a detail emerges that just violates the natural aesthetics of a comet. It's a glint of light, but it's not diffuse or scattered. It's a perfectly straight edge, a sharp, geometric line. Physicists identify this as specular reflection, the kind of clean bounce of light you get from a polished surface, not the chaotic scattering produced by a chunk of fractured ice and rock. This observation immediately brought to mind the work of researchers like Harvard's Avi Loeb and his Galileo project, which actively searches for extraterrestrial technosignatures. Independent analysts quickly ran the image through edge detection algorithms, which confirmed the anomaly, a line segment about 37 pixels long, presenting an angle and sharpness inconsistent with any known natural cometary phenomenon. The data pointed to a chilling possibility, that the light was reflecting off something manufactured. Data verification. In an age of digital manipulation, the first question is always, is the evidence authentic? This is where the power of modern data integrity and citizen science comes into play. Before any official statements were made, a global network of independent archivists had already secured the data. These individuals run automated scripts that continuously download and mirror raw data feeds from space agencies. Within minutes of the blackout, copies of the feed from Australia, Germany, and the United States were uploaded to public servers. Each file, carrying the identical 03:1712 UTC timestamp, was validated with a unique SHA-256 checksum. This cryptographic hash functions as an incorruptible digital fingerprint. Altering even a single pixel would result in a completely different hash. When every copy was compared, they were all identical. The chain of custody was flawless, from NASA's original relay to the decentralized archives. This rigorous process proved the anomalous frame was not a hoax or a transmission error. The data is immutable, the archives are clean, and the mystery, as the celebrated astronomer Carl Sagan often emphasized, is therefore deserving of serious scientific inquiry because the foundational evidence is verifiable by anyone. Technical explanations. If the data is real, could the blackout be a staggering coincidence? To answer that, we have to look at the technology involved. NASA's communications architecture is, a global machine. It relies on the Deep Space Network, or DSN, with its massive radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia. This system works in concert with the Tracking and Data Relay Satellite System, a constellation first launched in 1983, to provide continuous contact with probes and telescopes. Signal dropouts are a normal part of operations. As the Earth turns, a spacecraft will dip below the horizon of one DSN station, requiring a signal handover to the next. Sometimes this process, managed by engineers like JPL's Bradford Arnold, isn't perfectly seamless, causing a brief interruption known as a handover blank. These routine events are meticulously logged with specific reason codes. However, the outage at 0317 UTC, occurring at the exact second the anomaly was visible, did not have a standard handover code in the public logs. The official explanation cited general network instability, but the uncanny timing and lack of a specific technical fault code has left many experts and observers deeply unsatisfied. Digital forensics. Now let's zoom in to the pixel level, where the digital reality of the image is forged. Forensic analysis of the final frame revealed two critical clues that could point to a non-exotic explanation. First, the glint's straight edge aligns perfectly with the boundaries of several 8x8 pixel blocks. This is a telltale sign of how video compression algorithms like MPEG function. To reduce file size for transmission over vast distances, these codecs divide the image into a grid and can sometimes amplify or quantize a faint, noisy line into an unnaturally sharp, blocky one. The second clue involves cosmic rays. Deep space is saturated with high-energy particles that can strike a camera's sensor and overload a few pixels, creating a bright, transient streak that lasts for only a single frame. Digital forensics experts like Professor Hani Farid have documented how common these sensor-level events are in space imaging. Therefore, a leading theory proposes a double-hit scenario. A cosmic ray created a faint, linear artifact on the sensor, which was then exaggerated by the compression codec into the illusion of a perfect, solid edge. It's a plausible, purely technical explanation, though the brightness and consistency of the glint still push the boundaries of a typical artifact. 3I Atlas background. To truly grasp the significance of the anomaly, we must understand the object itself. Even before the controversial frame, 3I Atlas was a scientific puzzle. Detailed spectroscopic data from the James Webb Space Telescope, analyzed by teams including researchers like Martin Cordner at NASA's Goddard Space Flight Center, revealed a startling chemical composition. Unlike most comets from our own solar system's Oort cloud, such as the famous comet Hale-Bopp from 1997, which was rich in water ice, 3I Atlas was overwhelmingly dominated by carbon dioxide. It had a CO2 to water ratio of nearly 8:1. This means carbon dioxide ice, not water ice, was the primary fuel for its spectacular outgassing, creating a massive coma that stretched for hundreds of thousands of kilometers. This dense gaseous shroud completely hid the nucleus from direct view, with estimates placing its diameter at under a kilometer, comparable to the second interstellar visitor, 2I Borisov, which passed through in 2019. The Atlas survey's rapid scanning capability allowed for its early detection, giving us a precious opportunity to study it. This unique chemistry already confirmed it was an alien object, formed in a star system profoundly different from our own. Scientific scrutiny. In science, and especially in the search for extraterrestrial intelligence, skepticism is, well, the default position. Any extraordinary claim must survive a trial by fire. An anomalous signal in a single frame from one instrument is merely the starting point, not the conclusion. You see, the guiding principle is that extraordinary claims require extraordinary evidence. For the glint on 3I Atlas to be considered a credible techno-signature, it must be independently confirmed by other observatories using different instruments, preferably across multiple wavelengths of light. This is how science separates a true signal from instrumental noise or an artifact. As of now, the evidence remains on the lowest rung of this ladder of proof. We have a single, tantalizing data point, but no corroborating observations. Until the Hubble Space Telescope, the JWST or major ground-based observatories can produce matching data, the majority of the scientific community, including veteran SETI astronomers like Jill Tarter, will urge caution. It's a slow, rigorous process designed to ensure that when a discovery is announced, it is built on a foundation of undeniable, repeatable evidence, preventing the kind of historical misinterpretations like Percival Lowell's belief in Martian canals. 3 theories. The debate over the anomaly has coalesced into 3 competing hypotheses. The first is grounded in conventional cometary physics. Comets are chaotic bodies. The intense solar heating experienced by 3I Atlas could have caused thermal stress, fracturing the nucleus and cleaving off a large, flat shard of ice or rock. The unusual glint could be nothing more than a brief reflection of sunlight off this newly exposed, highly reflective surface. The second theory points to a technological illusion. This is the Occam's razor explanation, suggesting the edge is simply a convergence of unrelated phenomena. A cosmic ray striking the sensor at a shallow angle, its effect amplified and distorted by the video codec's blocky math. It's a ghost in the machine. But the third idea, the one that challenges our assumptions about the universe, refuses to be dismissed. This hypothesis, echoing the speculative work of physicists like the late Freeman Dyson, posits that the object is exactly what it appears to be, manufactured. Perhaps it's a component of a self-replicating von Neumann probe, a fragment of a light sail, or a piece of a protective shell. The odds are admittedly long, but the data is just ambiguous enough to keep the possibility on the table. Broader implications. An event like this, a mysterious signal followed by an unexplained data blackout, has consequences that extend far beyond the astronomical community. It becomes a catalyst for public debate and a driver of scientific policy. The conversation shifts from what is that object to who controls the data and the narrative of discovery. It amplifies calls for greater transparency and the development of open-source data platforms, a principle that is driving next-generation projects like Chile's Vera C. Rubin Observatory. For the public, it's a powerful lesson in critical thinking, reminiscent of the global reaction to the famous 1977 WOW signal. That powerful, unexplained radio burst detected by astronomer Jerry Amon remains a cornerstone of SETI lore. This incident with 3I Atlas forces a conversation about our technological and psychological readiness for a potential first contact scenario. It challenges international bodies like the UN's Committee on the Peaceful Uses of Outer Space to consider protocols for such an event. It perfectly illustrates the tension between rigorous skepticism and the profound sense of wonder that fuels our exploration of the cosmos. The search continues. So, where does this leave the investigation? The official record is clear on a few facts. At 0317 UTC, the NASA feed was cut. The final frame contains a cryptographically verified geometric anomaly. The blackout's timing, while officially attributed to network issues, is highly suspect. As of today, no conclusive, peer-reviewed evidence exists to support an artificial origin for the glint on 3I Atlas. However, the search for answers is accelerating. Ambitious new missions are already in development, most notably the European Space Agency's Comet interceptor. Scheduled for launch around 2029, this innovative spacecraft will park itself at a stable Lagrange point in space, essentially lying in wait for the next long-period comet or interstellar visitor to arrive. It will then be deployed for a close-range flyby, giving us our first high-resolution look at one of these pristine objects. This proactive strategy, championed by scientists like the mission's lead, Geraint Jones, demonstrates a paradigm shift in how we study these cosmic messengers. Every interstellar visitor is a gift, pushing our technology and our theories to their limits. The strange case of 3I Atlas remains one of the most compelling technological mysteries of our time. Caught between a plausible digital artifact and a discovery that could reshape the future of humanity. The verified data presents an anomaly, but the ultimate explanation is still out there, traveling through the darkness of our solar system. What is your analysis? Was this a ghost in the machine, a 1 in a billion natural coincidence, or our first fleeting data point from a technology beyond our own? Share your hypothesis in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the technology that is shaping our future. Thanks for watching InnoVision Tech. What if the third interstellar visitor ever discovered was not a comet, but a billion-year-old alien messenger? In the summer of 2025, a faint object designated 3I Atlas streaked into our solar system, and a controversial hypothesis immediately captured the world's attention. This was no ordinary rock. The idea of advanced alien technology made global headlines, but NASA quickly stepped in with a powerful, evidence-based response that settled the debate. So what did they find? Let's explore this together. The Atlas discovery in Chile. So, where does a story like this begin? It starts with our ever-watchful eyes on the sky. The story began on July 1, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey telescope at the El Sos Observatory in Chile detected a faint object with an initial apparent magnitude of plus 19.5. To put that in perspective, that's about 250,000 times fainter than what the human eye can see. When astronomers calculated its orbit, they saw something remarkable. Its path was hyperbolic with an orbital eccentricity calculated to be a staggering 1.8. In astronomy, any orbit with an eccentricity greater than 1 is unbound. This number confirmed it was moving at approximately 55 kilometers per second relative to the Sun, far too fast to be a member of our solar system. Astronomers quickly named it 3I Atlas. Initial estimates suggested it could be massive, between a few hundred meters and several kilometers across, making it potentially much larger than the previous 2 interstellar visitors. The discovery was a major success for the Atlas network, which also includes telescopes in Hawaii and South Africa, proving its effectiveness in spotting these rare cosmic travelers. The detection of a third such object in less than a decade confirmed that these visitors are more common than previously thought, officially opening a new frontier in astronomy. Avi Loeb's controversial hypothesis. Here's where the story takes a sharp turn into speculative territory, thanks to a bold proposal from Harvard astronomer Avi Loeb. While most scientists saw a fascinating natural object, Loeb, known for his controversial work on Oumuamua, offered a different interpretation. In a scientific paper posted to the ArcSiv preprint server, Loeb pointed to the object's early lack of a visible coma and its trajectory. He suggested that if the comet continued to show no outgassing, or if its path deviated from a purely gravitational path without a visible tail to explain the push, it could be evidence of something artificial. He even raised the hypothetical possibility of malign intent, though he stressed this was an intellectual exercise meant to keep science open to radical possibilities. His argument, similar to the one he made for Oumuamua, hinged on the idea that any non-gravitational acceleration without a visible coma required a novel explanation. He proposed that a solar sail, a thin, lightweight craft pushed by the pressure of sunlight itself, was one such possibility that science should not be afraid to consider, however unlikely it might seem at first. The physics of radiation pressure are well understood, but for it to be effective, an object must have a huge surface area and an extremely low mass, characteristics not found in natural bodies. Media sensation versus scientific method. You can imagine what happened next. The words alien technology from a prominent Harvard astronomer ignited a media firestorm. The idea was captivating, offering a sensational explanation for a new cosmic puzzle. But this is where the rapid world of headlines collides with the methodical, patient pace of science. The scientific method isn't about finding the most exciting answer, it's about finding the one that best fits all the evidence. The broader astronomical community, while not dismissing Loeb's right to speculate, emphasized the need for patience and adherence to Occam's razor, the principle that the simplest explanation is often the best. Their stance was clear. We must first rule out all known natural phenomena before jumping to an extraordinary conclusion. The use of preprint servers like ArcSiv allows for rapid dissemination of ideas, but also bypasses the traditional peer review process, meaning speculative ideas can reach the public before they are fully vetted by other experts. Ultimately, the scientific consensus held that declaring an object alien required the elimination of every single possible natural explanation first, a very high bar that had not yet been met. NASA's comprehensive investigation. With the debate raging, NASA and its international partners marshaled their most powerful instruments. This wasn't a casual glance, it was a coordinated, multi-platform investigation led by Tom Statler, NASA's lead scientist for small bodies. The agency dedicated priority time on the James Webb Space Telescope, using its near-infrared spectrograph or NIR spec, to perform detailed chemical analysis of the gases in its coma. Simultaneously, the Hubble Space Telescope's Wide Field Camera 3 was used for high-resolution imaging to search for any faint dust or fragmentation events with its superior resolving power in visible and ultraviolet light. On the ground, a network of observatories, including the twin 10-meter mirrors of the Keck Observatory in Hawaii, began a long-term monitoring campaign to track its brightness and trajectory with pinpoint accuracy. The goal was to leave no stone unturned, to precisely measure its path to within a few milliarc seconds, to analyze its chemical composition, and to study its light curve for clues about its shape and rotation. This multi-wavelength, multi-observatory approach is, honestly, the gold standard in modern astronomy for characterizing a novel object. Comet behavior confirmed. So what did this powerful array of telescopes actually see? The answer was unambiguous and came sooner than many expected. As 3I Atlas drew closer to the Sun, crossing the orbital distance of Jupiter at approximately 5.2 astronomical units, which is about 483 million miles, the solar radiation began to warm its icy surface. Just as predicted by standard cometary models, it started to sublimate, behaving exactly like a comet. Astronomers watched as it developed a distinct coma, the fuzzy, gaseous atmosphere around its nucleus, which grew to over 50,000 kilometers in diameter. Shortly after, a classic tale of gas and dust began to form. Tom Statler summarized the findings. It looks like a comet, it does comet things, and the evidence overwhelmingly points to it being a comet. The observation of outgassing with a dust production rate estimated at over 50 kilograms per second provided the natural explanation for any minor deviations in its path, rendering the artificiality hypothesis unnecessary. This behavior began right around the frost line where water ice turns to gas, a telltale sign of a natural cometary body. Chemical composition analysis. But confirming it was a comet was just the beginning. The real prize was in its chemistry. A team led by Dr. Anjali Sharma, a planetary scientist at NASA's Goddard Space Flight Center, used the James Webb Space Telescope spectrographs to break down the faint light from the coma into its chemical fingerprints. The analysis revealed familiar substances like water ice and carbon dioxide, but with a major surprise. 3I Atlas had an unusually high ratio of carbon dioxide to water, measured at nearly 35%. This vital clue suggested the comet must have formed in an extremely cold region of its home star system, far out in its protoplanetary disk, where CO2 could freeze out in large quantities. Furthermore, analysis of the dust grains showed a polarization signature with negative branching at a phase angle of 22 degrees, suggesting a surface composed of very fine, porous, fluffy dust grains, a sign of a very pristine, unaltered body. This fluffiness implies the grains have not been heavily processed by heat or collisions, making them a near-perfect sample of their native environment. This chemical snapshot provides invaluable data for models of planetary formation in other star systems. Trajectory and safety assessment. With the "what is it" question settled, NASA also moved to definitively address any public concern about its path. The coordinated tracking campaign from both space and ground-based telescopes allowed for an extremely precise calculation of its orbit. The agency confirmed that 3I Atlas posed absolutely no threat to Earth. Its closest approach to our planet will be a very safe 1.8 astronomical units, which is about 273 million kilometers or 170 million miles away. Its perihelion, or closest approach to the Sun, is predicted for January 12, 2026, at a distance of 1.5 AU, placing it between the orbits of Earth and Mars. NASA's Planetary Defense Coordination Office used this as a perfect real-world test of their tracking systems, proving they can accurately predict the path of even novel interstellar objects with incredible precision. After it loops around the Sun, its hyperbolic trajectory will ensure it is flung back out into interstellar space, never to return. Its brief passage is a fleeting but precious scientific opportunity. Natural anomalies in cometary physics. The whole 3I Atlas controversy really boils down to a single fundamental question in science. Is an anomaly evidence of something artificial, or is it a sign of a natural process we haven't encountered before? Science almost always bets on the latter. Our own solar system is filled with comets that behave in bizarre ways. Take Comet 29 P. Schwassmann-Wachmann, which can increase in brightness by over 15 magnitudes, a factor of 1,000,000, in just a few hours due to cryovolcanic eruptions. Another example was Comet C 2019 Y4 or Atlas, a different comet which unexpectedly disintegrated into multiple pieces as it approached the Sun, showing how fragile these icy bodies can be. The point NASA scientists made is that unusual traits are not automatic evidence of engineering. They are part of the normal, messy, and fascinating physics of icy bodies. These anomalies are not problems for science. They are the very data points that lead to new discoveries about how objects form and evolve. Thus, the unique chemistry of 3I Atlas isn't a paradox, it's a clue. Scientific value of interstellar visitors. So if 3I Atlas is not alien technology, why is it so important? Because interstellar comets are windows into other worlds. Each one is a preserved time capsule carrying the precise chemical and physical fingerprints of the environment where it formed. For 3I Atlas, the dominance of CO2 in its trajectory suggests it could be over 7 billion years old, originating from the Milky Way's thick disk, a population of ancient stars that existed long before our sun was born. By studying its isotopic ratios like the deuterium to hydrogen ratio in its water, scientists can get direct clues about the water in other primordial solar systems, a key factor in assessing the potential for life elsewhere. This is more than a curiosity, it is a preserved fragment of another planetary nursery. Future missions like the ESA's Comet interceptor are being designed specifically to launch and wait in space, ready to chase down the next interstellar visitor for an even closer look. These objects represent a fundamental shift from studying other solar systems through the faint light of their stars to analyzing actual physical samples. Comparing 3 interstellar objects. To truly appreciate 3I Atlas, you have to place it in context with its predecessors. The first, Oumuamua, discovered in 2017 with an eccentricity of 1.2, was a complete enigma. It was small, rocky-looking, showed no visible coma, yet had a mysterious acceleration. The second, 2I Borisov, found in 2019 with a high eccentricity of 3.37, was almost the opposite. Its nucleus was about a kilometer wide, and it behaved like a classic comet, allowing for detailed study. 3I Atlas, with its eccentricity of 1.8, falls between these extremes. It behaves like a comet, which sets it apart from Oumuamua, but its distinctive chemical ratios make it stand out from a standard comet like Borisov. This growing diversity is forcing astronomers to create a new classification system for interstellar objects. The current rate of discovery suggests that at any given time, there are likely thousands of interstellar objects within our solar system, but most are too small and faint to detect. As our technology improves, we can expect to find many more of these cosmic messengers, each one adding another piece to the vast puzzle of our galaxy. In the end, Comet 3. I-Atlas isn't alien technology, it's a natural interstellar comet, a stunningly beautiful and scientifically priceless messenger from another star system, shedding gas and dust as it speeds through our cosmic neighborhood. The real story here isn't science fiction, but the incredible power of science itself to solve mysteries and reveal the universe's secrets. It's a rare glimpse of pristine material from another world, reminding us that the cosmos is far more diverse and fascinating than we can imagine. For more deep dives into the mysteries of our universe, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting. Thank you for watching InnoVision Tech. What if the mysterious object racing through our solar system isn't what it appears to be? Fresh observations of 3I/Atlas are revealing characteristics so unusual that some scientists are questioning whether we're dealing with a natural comet at all. This interstellar visitor's trajectory, timing, and behavior patterns are defying conventional explanations, leading to heated debates in the scientific community. Today, we'll examine the mounting evidence that suggests this cosmic wanderer might be far more extraordinary than anyone initially imagined, and explore the controversial possibility that we could be witnessing something truly unprecedented. Discovery and initial detection. The story of 3I/Atlas begins with a routine sky survey that would soon turn extraordinary. On July 1, 2025, the Atlas Telescope system at Rio Hurtado Observatory in Chile captured images of an unusual fast-moving object designated A11PL3Z. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object. Within days, follow-up observations confirmed what astronomers had suspected. This was the third confirmed interstellar visitor in human history, joining the ranks of 1I Oumuamua discovered in 2017 and 2I Borisov found in 2019. The object received multiple designations, 3I Atlas for its interstellar status, and C2025N1 for its cometary characteristics. What made this discovery particularly intriguing was that despite entering our solar system weeks earlier, 3I Atlas had remained undetected due to its challenging viewing angle against the dense star fields near Sagittarius. John Tonry, principal investigator of the Atlas project, noted that pre-discovery images dating back to June 14, 2025 revealed the object had been silently approaching our solar system for an extended period. This late detection would prove to be just the first of many unusual characteristics that would set 3I Atlas apart from any cosmic visitor we'd ever encountered. Extraordinary orbital characteristics. Prepare to have your mind blown by the absolutely extraordinary orbital mechanics of this interstellar wanderer. Davide Farnocchia from NASA's Jet Propulsion Laboratory has calculated that 3I Atlas follows a hyperbolic orbit with an extreme eccentricity of 6.14, the highest value ever recorded for any known interstellar object. This mathematical measurement indicates just how dramatically different this visitor's path is from anything bound to our solar system. Even more remarkable is its incoming velocity of 58 kilometers per second, making it the fastest interstellar visitor ever recorded approaching our cosmic neighborhood. But here's where things get truly suspicious. The trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun. Marco Micheli from the European Space Agency has calculated that the probability of this alignment occurring by random chance is merely 0.2%. This isn't just unusual, it's astronomically improbable. Most objects from interstellar space would approach from random angles, yet 3I Atlas chose a path that seems almost deliberately designed for optimal planetary encounters. The precision of this trajectory has prompted some researchers to question whether we're witnessing natural celestial mechanics or something far more intentional. Such mathematical precision in cosmic trajectories typically requires either extraordinary coincidence or deliberate planning. Suspicious planetary encounters. The planetary encounter sequence of 3I Atlas reads like a carefully choreographed cosmic ballet that defies statistical probability. Robert Warwick from the University of Western Ontario, who previously discovered Oumuamua, has analyzed the object's path and found it passes unusually close to Venus, Mars, and Jupiter during its solar system transit. The probability of such close encounters occurring randomly has been calculated at an astounding 0.005%. Essentially impossible by chance alone. But the timing gets even more suspicious. Paul Chodas from NASA's Center for Near-Earth Object Studies has determined that 3I Atlas reaches its closest approach to the Sun precisely when Earth would be positioned on the opposite side, blocking direct observation during the most critical phase of its visit. The statistical probability of this alignment? A mere 7% chance. Karen Meach from the University of Hawaii has noted that rather than resembling the chaotic path of a randomly ejected comet, the trajectory appears optimized for studying the inner solar system planets while minimizing detection risks. This orbital choreography provides optimal vantage points for comprehensive planetary observations, exactly what you'd expect from a reconnaissance mission rather than a chance cosmic encounter. The mathematical precision required for such a trajectory suggests either unprecedented natural coincidence or deliberate design by an intelligence capable of interplanetary navigation. Physical properties and anomalies. The physical characteristics of 3I/Atlas are equally perplexing and honestly challenge our understanding of typical interstellar objects. Daryl Seligman from Michigan State University has determined that the object measures somewhere between 1 to 12 kilometers in diameter, making it significantly larger than both previous interstellar visitors and providing an unprecedented opportunity for detailed study. Spectroscopic analysis suggests this cosmic wanderer is extraordinarily ancient, potentially 7 billion years old, predating our entire solar system by billions of years. This makes it a genuine cosmic fossil, carrying secrets from the early epochs of our galaxy. Quanzi Ye from the University of Maryland has confirmed that 3I/Atlas is the brightest interstellar object ever observed, allowing for detailed spectroscopic analysis that just wasn't possible with previous visitors. Perhaps most intriguingly, the object exhibits a 29-hour rotation period with minimal brightness variation, suggesting either a spherical shape or a uniform surface composition, characteristics that are pretty unusual for natural comets. Matthew Knight from the Naval Research Laboratory has noted that high-resolution observations reveal a remarkably compact and dense appearance, lacking the typical fuzzy, diffuse structure expected from ancient comets. These physical properties suggest either an unusually well-preserved natural object or something with a fundamentally different composition and structure than anything we've previously encountered in our solar system. Comet-like features versus anomalous behavior. Here's where 3I/Atlas becomes truly enigmatic. It displays some comet-like characteristics while simultaneously exhibiting behavior that frankly just defies cometary physics. Alan Fitzsimmons from Queen's University Belfast has confirmed that the object shows a faint coma and a short tail measuring approximately 3 arcseconds, indicating active outgassing as solar radiation heats its surface. Spectroscopic observations have detected the characteristic signature of sublimating water ice, producing the dust and gas envelope typical of approaching comets. However, Tony Farnham from the University of Maryland has noted several anomalies that challenge this interpretation. Despite its proximity to the Sun and evidence of outgassing, 3I/Atlas maintains a remarkably compact, dense appearance that differs dramatically from the fuzzy, diffuse structure of typical comets. Most puzzling is the absence of an expected extended tail, which really should be prominent given the object's size and solar distance. Bin Yang from the European Southern Observatory has observed that the outgassing patterns don't follow standard cometary models, with irregular brightness variations that suggest complex subsurface processes. The combination of active sublimation with maintained structural integrity presents a paradox. How can an object simultaneously behave like a comet while retaining characteristics more consistent with a solid, engineered structure? This contradiction has sparked intense debate about whether we're observing natural cometary processes or something fundamentally different masquerading as a comet. Scientific debate: natural versus artificial. The scientific community has erupted into heated debate over the true nature of 3I/Atlas, with interpretations ranging from exotic natural phenomena to, well, potentially artificial origins. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University, has emerged as the most vocal proponent of considering artificial origins, pointing to the statistically improbable trajectory and suspicious timing as evidence that, in his view, warrants serious investigation. Loeb argues that the mathematical precision of the object's path, combined with its optimal positioning for planetary reconnaissance, exceeds reasonable expectations for random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide. However, mainstream astronomers have pushed back strongly against these suggestions. Sarah Seeger from MIT acknowledges the unusual characteristics while emphasizing the importance of exhausting natural explanations before considering extraordinary possibilities. Robert Yedecke from the University of Hawaii has criticized speculation about artificial origins as premature and potentially damaging to scientific credibility. The debate highlights fundamental questions about how we interpret anomalous data and the threshold of evidence required for paradigm-shifting discoveries. Alan Stern, principal investigator of the New Horizons mission, has noted that while the characteristics are unusual, the universe is full of phenomena that initially appear impossible until we develop a better understanding of the underlying physics. Spectral analysis mysteries. The spectroscopic data from 3I/Atlas is revealing some puzzling inconsistencies that are, honestly, challenging our understanding of interstellar object composition. Stephanie Malam from NASA Goddard Space Flight Center has been coordinating observations using the James Webb Space Telescope to conduct detailed infrared spectroscopy of the object's composition. Initial results confirm the presence of water-ice spectrum, but the patterns just don't match our expected models. Jacqueline Keene from Boston University has identified these anomalous spectral signatures, where the observed signals actually increase in regions where water-ice models predict they should decrease. This contradiction suggests either unknown compositional elements or maybe structural properties that don't conform to standard cometary models. Now the object exhibits a distinctly reddish coloration, similar to objects in our outer asteroid belt, yet its interstellar origin kind of rules out formation in our solar system. Michelle Bannister from the University of Canterbury has noted that attempts to determine precise composition are complicated by the active coma surrounding the nucleus, which creates interference in spectral measurements. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has suggested that these unusual spectral characteristics might indicate exotic ice compositions or internal structures not found in solar system objects. So, these spectroscopic mysteries really add another layer of intrigue to an already enigmatic visitor, suggesting that 3I/Atlas may be composed of materials or structured in ways we just don't yet understand. Dark forest hypothesis implications. The behavior patterns of 3I Atlas align remarkably well with theoretical models of how an advanced civilization might conduct reconnaissance while avoiding detection. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, suggests that intelligent civilizations remain hidden to avoid potential threats from other species. Seth Shostak from the SETI Institute has noted that 3Y Atlas exhibits what could be interpreted as stealth-like behavior, deliberately timing its closest solar approach when Earth would be positioned to block optimal observation. This timing ensures that the most detailed study phase occurs when our planet's scientific instruments have limited access to the visitor. Jill Tarter, former director of SETI research, has observed that the trajectory allows for comprehensive surveying of inner solar system planets, while minimizing exposure to potential detection by any resident intelligence. The orbital path provides optimal vantage points for studying Earth's atmosphere, Mars's surface conditions, and Venus's cloud dynamics, exactly the type of data an exploring civilization would prioritize. Frank Drake, creator of the famous Drake equation, noted before his passing that such reconnaissance patterns would represent logical exploration strategies for risk-averse civilizations. While most scientists remain skeptical of artificial explanations, the behavioral patterns of 3I Atlas do match theoretical models of how cautious interstellar explorers might operate when encountering potentially inhabited star systems. Historical context and lessons. The discovery of 3I Atlas comes with profound lessons learned from our missed opportunities with previous interstellar visitors. When 1I Oumuamua was discovered in 2017, the scientific community was caught completely unprepared for studying such a rare phenomenon. Robert Warwick, who discovered Oumuamua using the Pan-STARRS 1 telescope, has reflected on how the object's rapid departure left many critical questions unanswered. The mysterious acceleration exhibited by Oumuamua without visible outgassing remains unexplained to this day, highlighting the importance of comprehensive observation campaigns. Gennady Borisov, the amateur astronomer who discovered 2I Borisov in 2019 from his observatory in Crimea, provided the astronomical community with a second chance that was better utilized. However, even Borisov's study was limited by available technology and coordination protocols. Mark Norris, from the University of Central Lancashire, has emphasized that 3I Atlas represents our most comprehensive opportunity yet to properly study an interstellar visitor with advanced instruments and coordinated global observation campaigns. The improved detection capabilities of modern sky surveys, combined with rapid communication networks, have enabled real-time coordination among observatories worldwide. Michelle Bannister has noted that the lessons learned from previous interstellar encounters have fundamentally changed how the astronomical community approaches these rare events, ensuring that we're better prepared to unlock the secrets these cosmic messengers carry from distant star systems. Future observations and implications. The coming months represent a critical window for determining the true nature of 3I Atlas before it departs our solar system forever. Perihelion is scheduled for October 30, 2025, after which the object will begin its journey back toward interstellar space. Paul Chodas has calculated that 3Y Atlas will re-emerge from behind the Sun in December 2025, providing a final opportunity for detailed observations before it becomes too distant for meaningful study. Karen Meach is coordinating an unprecedented international observation campaign involving over 50 professional observatories and numerous space-based instruments. The Hubble Space Telescope, James Webb Space Telescope, and ground-based facilities including the Very Large Telescope in Chile are all dedicating precious observation time to this cosmic visitor. Daryl Seligman has noted that the data collected during this campaign will either confirm 3I Atlas as an exotic but natural interstellar comet, or potentially revolutionize our understanding of what's possible in our cosmic neighborhood. The implications extend far beyond pure astronomy. If 3I Atlas proves to be artificial, it would fundamentally alter humanity's perspective on our place in the universe and our approaches to planetary defense and interstellar communication. Alan Fitzsimmons emphasizes that regardless of the final interpretation, 3I Atlas represents a pivotal moment in astronomy, where advanced technology meets unprecedented opportunity to study materials and possibly intelligence from beyond our solar system. As 3I Atlas continues its mysterious journey through our solar system, it challenges everything we thought we knew about interstellar visitors. Whether this ancient wanderer is an exotic natural phenomenon or something far more extraordinary, it's forcing us to expand our understanding of what's possible in the cosmos. The next few months will be crucial in determining the truth about this enigmatic visitor before it disappears back into the depths of space. Stay tuned to InnoVision Tech for the latest updates on this cosmic mystery. Share and subscribe. What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the James Webb Space Telescope. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The singularity itself represents a point where our laws of physics break down, which is deeply unsatisfying for physicists. The model also struggles to explain why the universe appears so uniform in temperature over vast distances, a puzzle known as the horizon problem. Furthermore, the geometry of space is remarkably flat, an initial condition that seems incredibly fine-tuned and lacks a complete explanation. The black hole universe theory. What if there's a more elegant explanation, one that doesn't require inventing new particles or mysterious forces? A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles like electrons cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. The strength of this pressure is truly staggering. It's the only known force capable of halting the complete gravitational collapse of a star's core. While we observe it in stellar remnants, applying it to a collapsing universe is a theoretical leap, but one grounded in established quantum principles. The crucial assumption is that these quantum rules hold true even at the unimaginable energies and densities of a universal collapse, providing a physical barrier against infinity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe, captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet, JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that Standard models struggle to explain so soon after the Big Bang. Under the Standard Model, the universe's gas simply wouldn't have had enough time to cool and condense to form such massive structures so quickly. It's like finding a fully grown ancient oak tree in a field that was barren just a week ago. The timeline doesn't add up. These pre-existing black hole seeds would essentially give galaxy formation a massive head start, neatly explaining the presence of these cosmic anomalies. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin, an alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light-years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light-years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations describing the space-time around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole. From the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. From the outside, in the parent universe, our cosmic time would appear to be frozen at the event horizon, a classic effect of gravitational time dilation. Conversely, from our perspective inside, time flows normally, and it's the parent universe that is inaccessible to us. This fascinating duality means that our vast, dynamic cosmos could appear as a static, timeless object to any potential observer in the universe that spawned it. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of spacetime called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, spacetime can bend but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers, but creators. In Einstein's general relativity, gravity is described as the curvature of spacetime, like a heavy ball on a rubber sheet. Torsion adds another geometric property, a twist or spin to the fabric of spacetime itself, which only becomes significant at extreme densities. This twisting effect would act as a repulsive force, preventing matter from collapsing into an infinitely small point, and instead causing it to rebound outwards with tremendous force. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the Oumuamua satellite, and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech.